All right, good afternoon, everyone. Welcome to our NEUTC webinar series. We're really excited to jumpstart 2025 with our webinar series here today. Before we get into Dr. Weng's presentation, I just want to give a quick background in terms of who we are as NEUTC. So the New England University Transportation Centers, we are a Region 1 UTC, so up here in New England. Just for context sake, UMass Amherst, we are the lead of the UTC that was awarded back in 2023. In addition to us here in Massachusetts, we have MIT, Bunker Hill Community College, and Holyoke Community College on our team. And then outside of Massachusetts, we have the University of Connecticut, Norwich University up in Vermont, University of New Hampshire, and the University of Maine, all on our team. We're really excited to bring to you this webinar here today. Our mission at NEUTC is really to advance safety through transformational research, education, and technology transfer. And a handful of our themes on hand are embedding community engagement with transportation safety, developing smart infrastructure connected systems, promoting automated vehicle safety, and improving safety for all modes and transportation populations. So we're really excited to host this webinar here today. We finally had some of our year one projects wrapping up this past the end of 2024 here, and we're excited to see a highlight of that here today. So just a quick introduction for our speaker today. So Dr. Meng Weng very recently completed her PhD out here at University of Massachusetts in the Mechanical and Industrial Engineering Department, focused in industrial engineering. We're very excited that now she's on the West Coast. She's now working for Waymo as a software engineer. We're very excited for her to talk today about her project. So Meng, the floor is all you. Actually, before I hand it over to you, I just want to note, so there is a QA function at the bottom there. So if you have any questions throughout the presentation, please feel free to populate that. When we get to the end of Meng's presentation, we will go through that Q&A list. We'll go probably about 20 minutes or so. We'll do a Q&A, and then we'll get wrapped up with that. So Meng, the floor is now officially all yours.
Thank you, Francis. Yeah, so hello, everyone. My name is Meng. I just graduated. I just successfully defended my dissertation last month. So it's been just a month from now. And I'm very excited to present my last chapter of my PhD dissertation, which is also funded by NEUTC. So I really appreciate this opportunity for me to present. So the title of this work is called "The Context of Crash Occurrence," and it's going to be a framework that combines a complexity-infused approach that integrated semantic, contextual, and kinematic features of the driving dataset. So let's start with a bit of a background here. So to enhance traffic safety, we first need to understand what are the causes of the motor vehicle crashes. And there was a study conducted on around 5,000 of crashes, and they found out that a lot of the crashes were due to the driver related or driver interaction related crashes. And the percentage was 74%. And among this, a large majority of the driver interaction related crashes, there were two main reasons that are attributed to this reason, which are recognition error and decision error. The recognition error usually was caused by inattention, distraction, and inadequate surveillance, and decision error usually attributed to driving too fast for the conditions, false assumption of others' actions. And here in this presentation, I'm not going to deep dive too much into why this causes happens, but more from one specific aspect, like the scene of the driving complexity. Like the scene itself can be very complex, and that causes the recognition error of the drivers, and also that complex scene may cause the drivers to drive too fast for the conditions, so on and so forth. So here I'm just going to confine my definition here that the recognition error is closely linked to the characteristics of the roadway scene, and that can affect the driver's cognitive load, and they can also affect drivers' ability to maintain their attention level. So here are a few examples that I want to show you. The first one on the top left side is a very clear scene with no traffic there. So you can feel like, oh, if you are a driver, the scene can be very low complexity and you will feel very comfortable driving in such conditions. And on the second one, it has still a clear weather condition, but it has more moderate traffic conditions. So if you are a driver in this scene, you feel like, oh, it's gonna be more complex and you need to maintain a higher level of attention to maintain this driving task. And for the third case here, the traffic is very similar to the first example, but it has a raining weather. So the weather condition can be another aspect and can be another effect on affecting the driver's behavior and attention level. And the fourth is a clear weather, but with moderate traffic condition and nighttime. So it brings the complexity level to the highest level among these four cases. So here we can see that the traffic condition, the weather condition, and the time of day can affect the complexity of the driving scene. And so I try to classify those conditions into several categories. The first category is called semantic information that usually will be defined as the number of objects around the ego vehicle. And second can be the contextual information, and that contains everything on the road that is related to the context. For example, the roadway type, road curvature, weather, time of day, and everything like the lane width. So the combination of these two information, semantic information and contextual information, can be put them together and be defined as a scene complexity. So this is how we define scene complexity in this study. And secondly, with the scene with the scene where changes as time goes by when you drive on the roadway, the driver's behavior will also be affected by the complexity level of the scene. So for example, if you as a driver see the very complex scene, you will naturally brake, you will naturally reduce the speed. And when you are driving in a very comfortable environment, you will naturally drive faster or have better maneuvers in changing your behavior or in just like less speeding or less braking behavior. So there is some kind of intrinsic relationship between the scene complexity and the driving pattern. So here in this problem, we further define roadway complexity. That is actually the combination of the scene complexity and the driving pattern. So here I'm going to introduce the methods of how this scene complexity and driving pattern are extracted from the study. So here is the first semantic feature generation. So with the advancement of the computer vision models, we're able to extract the pixel level of predictions of the driving scene. So for example, in this example here, you can see for the scene as a driver, you will be able to see, well, where the car is and where the road is and where are the boundaries are. And the model can also do the similar thing for us. And with that prediction, we are able to generate pixel level predictions. And the percentage of the pixels of each class was calculated. And some example classes are car, pedestrians, and vegetation and sky and road. And also with some closed objects, we are able to calculate the number of objects. So we can see as a good example here is the more cars in front of you, you will have more difficulties in maintaining or in paying attention to the surroundings. So we are also going to calculate the number of objects of each closed object. And to further get the attention region of the driver, the lead car region was identified and adjusted based on the vehicle model. So we can see there's it's being shown in the green box here, and the lead car region is a little bit different for the different car models, and that are all being calculated in this case. And so we just discussed the semantic features generation, and the second part was the contextual feature generation. And I just said the contextual features include the weather conditions, traffic conditions, road conditions, visibility, road layout, so on and so forth. And all of these features can be generated by the large language model. So it's really a prompt thing, like we can input our image as well as our prompts into the large language models, and they will give us the output. So for example, here in this image, the weather would be clear, traffic condition would be moderate, road condition would be dry, there's no rain, visibility is pretty clear. Road layout is straight. There's no curve, and road type is highway. It's not in the residential area, and road width is pretty wide. It's not in the narrow, in a busy street. So we are able to generate search of these 7 features for all of the images that we have in the data set. And the third, it comes to the kinematic feature generation. Kinematic features contains speed, acceleration, and some of the derivations. So for example, in speed, we are able to calculate the mean standard deviation. Acceleration, we also have the mean standard deviation, minimum, maximum, and the deviation from the speed limit. So because it's a mean, well, it's more like a statistics measurements of the data. So we are doing a fixed distance extraction method. So the original data comes with a video clip. It has a like 10 seconds, 20 seconds, and we try to extract like each 20-meter segment by a fixed distance. And then for each segment, for each small segment, we calculate the mean standard deviation of the speed, acceleration, so on and so forth. So all the video clip are then translated into small segments, and then they are translated into statistics measurements of their kinematic features. So I just introduced the 3 feature sets, the major 3 feature sets that we generated from this study, and I'm going to introduce a data set that is being used in this study. This study used the MIT ABT dataset, and we selected 5 video clips from the original dataset. And thanks to their preliminary experiments, they were able to extract some high-level context information, and I took the advantage of that. So I specifically selected 100 highway cases, 100 rural cases, 100 urban cases, and 75 bridge, 75 overpass, and 50 crash hotspots. So the hotspots I'm going to explain that later in these slides. But here is just I kind of want to control have a stratified selection of the data set so that we can have a kind of a balanced distribution of the video clips. And in terms of data modality, we have the video data that can be used to extract the context or the semantic features. We have the canvas data that can be used to extract the kinematic features, and GPS data that is going to be used for extracting the crash hotspots. And because it was a fixed distance sampling method, the final data set consists of around 10,000 frames. So in terms of the ground truth that is being used here, the first one I collected was called complexity index. So the complexity index is just a quantified way to let the people or to let AI to annotate how complex they think that the environment is for them to drive on. So here are the 2 user interface, or the 2 examples here that I interact with. I use the Amazon Mechanical Turk and the language model again to annotate the numeric value. So the complexity index is basically just a scale from 1 to 10, 1 being the least complex, not complex at all, and 10 being the most complex, overwhelmingly complex. And during this annotation collection process, we also collected the multiple annotations for each image to ensure data quality. And for this multiple annotations, the human annotations were taken as an average of every annotation, and the AI annotation was finalized by taking the majority vote. And secondly, we have the crash likelihood that is extracted from the historical data from the Massachusetts database. So because the MIT dataset doesn't contain any crash events, so I extracted historical crash data from 2018 to 2022. That was a 5-year period. And I also applied a kernel density estimation to generate a continuous scale of the crash likelihood. And as you can see from this heat map, the red dots represents there are a lot of crashes happened in the past 5 years, and that is how I defined crash hotspots. And the blue dots represents the 10,000 cases extracted from the MIT AVT dataset, so that we can map the dots on the heat map so that we can extract that continuous scale. And from the histogram, on your right-hand side, you can see the distribution of the crash likelihood is pretty skewed. So to keep the class being balanced, like the crash likelihood between 0 to 0.5 is defined as low crash likelihood, and anything between 0.5 to 2 will be defined as medium, and everything above 2 was defined as high crash likelihood. Okay, so I just defined, or I just explained how we extracted features, how we annotated data, and collecting the ground truth. Then I'm going to explain how the method is being used here. I would like to bring up a concept is called encoder. So an encoder is essentially a one layer fully connected neural network that is trained on the three feature sets: the semantic, kinematic, and contextual feature sets. And the response was the complexity index. So it's just a modeling part. And with the neural network structured with their natural structure, we're able to extract the latent complexity layer from the encoder structure, and I'll just refer it to complexity-infused features in this case. So essentially, we trained the encoder here. The input was the three original data sets, and output was the complexity index annotated by AI or human. And we will use the latent complexity features later on in our second phase of the modeling part. So here is an overview of the methods and everything that I just explained. To put them together, we started with a raw data being collected from the camera and the vehicle sensors. Then we extracted the semantic features by applying the computer vision model. We extracted kinematic features from the CAN bus data, and we extracted the contextual features from the large language models. Then we collected complexity index from both AI and human, and we first calculated the complexity-infused features by applying the encoder on this original data sets, and then we combine these complexity-infused features back to the original feature sets. That is being said, semantic features, kinematic features, and contextual features. Then these four features together will be used to investigate how that are correlated to the crash density, crash likelihood that is being shown previously in that heat map. So this is an overview of the methods, and then I'm going to explain how the data are being analyzed here. So a little bit details on the encoder. We found out that using 32 neurons, using the LLM data will have the best performance. And there is a preprint version of this paper that you can look for later on so that you can have more details of how we selected the parameters of the encoder. And the second part is when evaluating the crash density prediction model, in the second phase, we tried multiple models that includes random forests, gradient boost decision trees, k-nearest neighbors, and neural network models. And the best model will be reported based on the accuracy. And the baseline models were trained on just original feature sets. And the final models were trained on incorporating the latent complexity feature into the original feature sets. And we are going to compare how much improvement by incorporating that complexity-infused features. And the goal is just to compare the performance between these two models and see whether the complexity-infused features really improve the performance. And also, on top of the main analysis, there are a few ablation studies. The first one is model comparison. Like we compare the performance of models trained on the original feature sets with those incorporating the complexity index. And also for the best performing model, we have a feature importance analysis that is being evaluated by the chef value. And third is comparing the AI and human annotation. So like I said, like the encoder trained on the AI data will have the best performance, but I'm also going to show you how that difference will be. So let's jump into the main results here. There are a few experiments being conducted here, and there are essentially three combinations of feature sets. The first one is just semantic, and the second one is the semantic and kinematic, and third is the combination of semantic, kinematic, and contextual features. So from the baseline column, we can see that the performance will always better as we bring more feature. So that means first we want to bring as much available features as possible so that we can improve the model performance. And secondly, if we add the complexity-infused features to the original features, there is also consistently an improvement in terms of the accuracy of the model. So that further indicated that in complexity-infused features will have a positive impact on improving the model performance, in understanding how the crash happened in the past. So that is the main results. And the second is the comparative studies. So well, you might ask, what's the point of using that complexity infused features? You already have a complexity index. So why not you just add them to the original features and see how that performs? Yes, and we did that experiments, and we see that the complexity index itself didn't improve the model too much. So we can see here it the results didn't change too much. So that further indicated that we need to extract some hidden information from the complexity index and the original feature sets to improve the model performance. And third, the feature studies. It's a SHAP plot, and essentially it shows for each class, well, this is a 3-class classification problem. So it shows for each class how the features are associated with that corresponding class. So if we see, for example, if we want to differentiate low versus medium crash density area, and the vegetation and the rural area appears to be the most significant ones. So for example, like more vegetation will lead to lower crash density, and more rural area, well, like rural area is associated with lower crash density, and that really makes sense to us, right? And in terms of the high crash density areas, we see that there are some of the speed-related features and highways, and we can see, especially here, highway are usually associated with a higher density, crash density. So that also makes sense to us. And in terms of comparing the low versus high crash density areas, we can see there appeared to be a latent complexity infused feature. We don't know how that really matter or how that really will affect the model performance, but there appear to be one, at least one. So we see that, okay, the complexity infused features is really playing their role here by differentiating different levels of the crash density. And last but not least, the ablation study. I just mentioned that the previous results use a complexity index from the AI, from our large language models. And how about we do the same thing by replacing that complexity index annotated by human? And we can see here, if we rely on the results on the complexity infused features and the baseline models, the LLM data perform better. Well, it has a better predictive ability in terms of predicting the crash density. And if we just use a complexity infused feature alone to investigate the relationship with the crash occurrences, the MTurk data will have slightly better performance. So it's a I cannot say that AI is better than human in all times, but it's just based on how you choose the features and how you like to define the problem, and also as well as the cost of collecting data. So here it's just for your information here. So to conclude, This study introduced a two-stage framework. The first stage was to extract the hidden features from semantic, kinematic, and contextual features. And the second stage is to using this hidden feature and original feature sets to investigate the relationship between the crash occurrences in the historical data. And it achieved like 90% of accuracy in correlating that with the historical crash data. And also, to recap, to differentiate low versus medium, the semantic features and the contextual features are being the most important. And for the high crash density areas, there are some vehicle kinematic features and the contextual features are being pretty influential. And to differentiate between low versus high density areas, there appear to be at least one complexity-infused feature. So that means to bring them together, all of these feature sets are pretty useful in understanding the crash occurrences, and that means it's very important here for us to consider how we want to better mitigate the crash occurrences in the future. And also, the data generated by large language models and human have different capacity in understanding the crash occurrences by using different sets of the features. So we also need to keeping that in mind. And the potential applications include we can develop HMI related applications such as warning systems and driver monitoring systems to better understand the scene and how the scene will affect drivers' cognitive load, drivers' behavior, so on and so forth. So here concludes my presentation, and I again want to thank NEUTC for their funding opportunity. I really appreciate that they will let me to have the opportunity to work on this project, and I also want to thank MIT AVT dataset. They share with me the data, and I also want to thank my advisor, Professor Jenna Roberts, for her support and advising throughout this project. And thank you. I'll be happy to take any questions you have.
Awesome. What wonderful presentation. We have a handful of questions here, so I'll just start rattling them off. So a quick one is, did you control for traffic volumes at all? I know you noted, I'm going to paraphrase on this one. I know you noted the higher density or higher complexity or high crash density areas. Was there any traffic volumes controlled? The person says crash hotspots tend to be at areas with more traffic, so you may miss high crash locations and rural locations if volumes aren't considered.
I just want to clarify here. So the traffic volume here, that is connected to the crash occurrences, or that is related to the data that I used for feature extraction.
Awesome. Another one here is there a way to potentially automate initial countermeasures that might counteract high complexity locations that translate into higher crash densities?
To automate initial countermeasures that might.
So I think in other ways, are there a way to automate these initial steps of identifying the countermeasures in order to counteract these high complexity areas?
Can you give me a few examples of what are the countermeasures are?
You know, I'm going to have that person reiterate that one for us.
Okay.
I'll go to the next one. We'll jump back to that one. How do
Okay.
you see how do you see this research being applied in the real world? For example, how can car manufacturers use this information to better design vehicles?
Yes, I think they can definitely be applied in the real world situations, because the feature extraction part can be definitely by introducing some built-in models, embedded models in the vehicle, so that we are able to extract some of the semantic features, contextual features, and kinematic features. And then if the vehicle is connected to the database, and it has knowledge of whether this is a high density area, a high crash density area, it will know like how that are associated together. And in the future, once the model are finalized, we don't need that crash information anymore. We just need the scene information and the kinematic information. And with that information, it will be able to issue a warning message when it goes to a potentially high crash density area, and that can definitely improve the traffic safety.
And then actually dovetailing off, that's great. Dovetailing off that is, are these features something that can be used by, say, electric car companies to help make things like self-driving cars safer?
Yes, yes. Well, I was speaking from what my working experience at Waymo so far. So like they're definitely are using the features that are identified on the road. For example, the vulnerable road users. This is our top priority for them to pay attention to. And second is anything that goes in the lane that the vehicle cannot drive through. So anything that will in affect the driver, self-driving car, or even the driver will be considered as a very high priority to be detected, to put a very high risk label. So I think like from the scene, there are a lot of information out there, and the cars and the human really want to understand whether the scene is safe for us to drive. So yeah, that is going to be very useful.
Certainly. And then so rephrasing this question back. So is there a way that you could make recommendations of lowering the complexity once you've identified these high complexity locations? Is a different way of asking the question.
Oh, yes, yes. So, for example, for the high density regions, we see that it's usually associated with highway. So we know that driving on the highway is unsafe, or for some of the cases. So we might want to further investigate how the highway, in which situation the highway will be associated with high crash density occurrences. So then we can bring some um, measures to improve the traffic safety on the highway. Does that answer this question?
I believe so, yeah. Yeah, no, that's great.
Yeah.
Okay, we got another one that just came in. What about things like animals or unexpected obstacles that happen in front of drivers? How can this information help detect unsuspecting obstacles?
I, well, yes. So I believe in that computer vision model that extract the pixel level generation, it has a class that being labeled as another. So at being labeled as an other. So if we leverage that other class, or we can first have a sense of whether there are some unexpected things that is going on around us. And second thing that I came to my mind is we can try to improve the classes that's being available from that model. So if they can bring more people to triage or to annotate these unexpected obstacles, then it can improve the computer vision model performance. And on top of that, we will have understanding of how much obstacles is around us.
All right, got a couple more here. And again, anybody, if you have any additional questions, please populate them in that Q&A chat. So how do you think your findings would have been different if you had sampled in a different way? For example, if your sample had more overpasses or rural roads as compared to, the highway sample.
I I believe that is going to be slightly different. Mm, so But I think the next step in this study is we want to bring more samples in this feature in this study, and we want to try different models on different distributions of the data sets. So that is really going to be different, but I don't know the answer yet, and I think it's worth exploring. And the motivation of I try to control that distribution is just because they already have that annotations available, and there are some preliminary studies that found, okay, so for this one and for this one, for overpass and for underpass, they may have different behavior. So I just want to control that distribution. But I think that is really worth exploring as part of the future work.
And then possibly dovetailing off of additional future work or are you aware of any research out there that discusses the different driving populations, for instance, older and younger drivers, and how they may fit into and fit into this?
Yeah, I it's well, because for this data set is the kinematic data are just from the drivers that are being recruited in that study, in the MIT ABT study. So we really don't have much control here to control the population of the drivers. And also, I think the population will like how human drive differently will have an impact on their kinematic measurements. But also, I want to emphasize here that we also going to extract the semantic and context information that is irrespective of the driver's population. So that will have some impact, but I foresee that it will not change the results too much. But it's also worth checking like how the behavior itself will affect the will be correlated with the crash occurrences.
And then, just out of curiosity, I guess I have a quick one. So with your mechanical Turk data,
Yes.
what were the types
Yes.
of parameters you had to set in using? And then what was your sample for that, just out of curiosity?
I restricted the participants or the annotators to be reside in the United States, and they have to hold a valid driver's license. So these are the conditions.
Gotcha. Okay, we have another one in here. How do you handle the fact that a growing share of crashes involve vulnerable road users and larger vehicles? Studies have shown that today highways are some of the safest roadways, while collectors, arterials, and local roads are more dangerous to people, primarily because of these vulnerable users, road users. Is there a plan to include VRUs, vulnerable road users, in your study in the future, or to focus on this in the future? I guess this goes on some future work ideas.
Yes, and I think it's definitely worth checking because for now, the crash occurrences are just defined by the historical data, and there is no further classification of why these crashes happened. I just like include every vehicle crashes in the heat map. And if we can try to dif differentiate, for example, these crashes happened due to hitting the vulnerable road users, and these are caused by speeding on the highways, then I believe there will be some different conclusions that can be drawn from the study. So I think it's definitely worth checking as part of the future work.
Awesome. So that's all the questions I'm seeing in here. If there's any last one, I'll give you a couple of seconds left, but thank you so much, Dr. Weng, for the presentation today. This has been fantastic. We really appreciate your time presenting this work. It's really fascinating work. Um, Thank you all for attending today. We are very excited to keep the train rolling with this webinar series. We'll have another webinar slated 1 month from now. So March 27th at 3 p.m. We'll be sending out that information. We'll try to get it in the chat before we get things closed here for that webinar next month. So thank you all for attending, and I hope you have a great rest of your day.
Thank you.